Hello everyone, today I'll be showing you guys how to solve the Schrodinger equation for an n-body part problem. Okay, so the Hamiltonian for an n number of particles is this, right over here. Okay? I also want to note something. For an n number of particles, the wave function, it has an n number of inputs, right? So for the one particle case, so you have one particle at x, we just have psi of x, right? Describing everything that we can know about that one particle. But for multi-particles, we'd have like x1, x2, x3, x4, and so on. And we just have one big old wave function, psi of x1, x2, x3, and so on, that describes all the particles collectively. Alright? And here we are assuming that the masses of all the particles are identical. If they aren't identical, then we are gonna see a 1 over m n in this sum over here. But yeah. Okay, so actually I'm going to show you guys how to solve this for the n equals 2 case. But it generalizes quite easily and quite trivially to any number of particles. So hope you guys can follow along in this video. So for n equals 2, our Schrodinger equation, or equations, I guess you could say, is this over here. Okay, now this equation is pretty convoluted, and it's going to be pretty difficult to solve for the general case, because it is a two-body problem, right? And we are solving for psi of x1, x2 here, right? So we can make this equation simpler if we we can separate it. In other words, if you make a couple of assumptions. Now these only hold when our assumptions are met. Number 1, we assume that psi of x1 and x2 is separable, like we always do in physics. So we have psi of x1 times psi of x2. Number 2, we assume that our potential v of x1, v of x2 is also separable as a sum. So v of x1 plus v of x2. And this only applies when the particles do not interact. So if they do interact, this assumption no longer holds. But with these two assumptions, we can actually make this equation really simple to solve. So let's get into it. Okay, so first of all, we have to plug in psi of x1 times psi of x2 for big psi. So minus h squared over 2m, second derivative, psi of x1, psi of x2, plus the potential psi equals e psi. Now, we can actually move these terms to the front, since the derivative at the front of it evaluates only the other term. So you would get minus psi x2 h bar squared over 2m, second derivative of psi of x1 minus 1 over psi of x1 h bar squared over 2m, second derivative of psi of x2 plus v psi x1 psi x2. Should have put psi of x1 psi of x2 here, by the way, equals e psi of x1 psi of x2. Alright? Now we can actually just divide both sides by psi of x1 psi of x2, and these go away. Oops, silly me. Okay, don't know why. This should be a psi of x1, not 1 over psi of x1. But related to that, we can divide both sides by psi of x1 psi of x2, That should be psi of x1, psi of x2, by the way. Just being a bit lazy today. This is going to be a very long video. So we divide both sides by that. So these go away. And these pick up a 1 over psi of x1 term. And this side picks up a 1 over psi of x2 term. Okay? So now we have minus 1 over psi of x1, h bar squared over 2m, second derivative of psi of x1, minus 1 over psi of x2, h bar squared, 2m, second derivative, x2 coordinate, psi of x2, plus v equals e, yeah, and this is gone, by the way. So we see that this entire thing equals one constant, by the way. Okay, all right. So here is where we plug in the separability of the potential. So remember that the potential can be separated into two terms. Well, we assume it can. V of x1 plus v of x2, right? And that equals e psi. So not e psi, just e. So now, note that E is a constant, right? So we can actually split the energy into two terms and add them together, right? So I'm going to split our energy into two terms. Let's call them epsilon A and epsilon B. Now also note, this is not an assumption. This works for all constants. You can just take them, separate them into two terms. Like, I'm not saying that E is dependent on x1 and x2. We are not saying that. We're just saying that E can be separated into two constants, right? So here, E is defined as epsilon A plus epsilon B. And you're going to see why we're doing this. You probably already see that. We can actually pair these terms with these terms. Like we can set these terms to be equal to each other. And then we can also make these terms and these terms be equal to each other. You can do the algebra for yourself, but we can set the corresponding parts to be equal to each other. So now we'd have minus 1 over psi of x1, h bar squared for 2m, that's taking derivative of x2, 1, psi of x1, plus v of x1 equals epsilon a, and we have minus 1 over psi x2, h bar squared over 2m, second derivative x2 coordinate psi of x2 plus vx2 equals epsilon b. We can then multiply both sides by psi of x1 here. So when we do that, we get a psi of x1 here. This might be a bit squishy, but we have epsilon a psi of x1. All right. So let's just leave that a bit more. Erase this part. Bring the minus back. This is just all aesthetics. Just ignore this part. Oh yeah, this should be equal. Sorry, I equal epsilon a psi of x1. And this is plus this. All right. This is not aesthetics. You do the same thing here. You multiply both sides by psi of x2. Where this goes away. Minus goes here. Now we have plus v of x2 psi of x2 plus epsilon b psi. Alright, now this part is just aesthetics here. Okay, epsilon b psi of x. Alright, so we have seen that we have successfully reduced our one equation to two separate equations. So we took a two-body problem and made them into two one-body problems, which are much more easier to solve here. All right. So yeah, that's basically how you do it. And note that again, psi of x1, psi of x1 and x2 It's just a product of each term in that matter potential. V of x1, V of x2 was just V of x1 plus V of x2, and that our energy is defined as epsilon A plus epsilon B. All right. So yeah, that's just how you do it. You can probably see how this works for 3 particles, 4 particles, and even n particles. Just add another line there. So yeah, that's how you do it. Also, I want you guys to try to solve the solve the Schrodinger equation for 2 particles and the free particle potential where V of x equals 0, and solve it for the case where our 2 assumptions hold, and we can find the overall wave function. I want you guys to do that as homework. It's pretty simple. All you really do is that you just make all these you just cancel out these terms, not cancel out, but like these terms go to 0 because the potential is 0, right? Yeah. Solve it for vx1 x2 should be 0. Yeah, and you just solve you just solve the 2 equations, then multiply the resulting wave functions. You can probably even do it in your head. It's not really hard to do, but yeah, just do that and get the total wave function so you can actually see this happening in practice. So yeah, that's how you do it. My next video, I think it might be on L infinity spaces, maybe like QFT. So just let me know what video that you guys want to see next. So yeah.